Welcome everyone. Now finally time has come to discuss the single slit diffraction. So far we've been hiding this problem by saying that slit is each slit is a small circle, source of a spherical wave. Although when we did the diffraction grading, we actually considered a long groove, but still we didn't actually think about its thickness. And so now it's time for us to really confront what is actually a single slit, and what's the diffraction effect from that. So in order to discuss this, let's see. Let's put this slit plate, and then let's put this screen. Let me actually use the coordinate system in such a way that we used to let's use this as x or y. How about this as x, and then that will be c. So the screen is in the yz plane, and x is the line that connects the screen and the slit plate, and this length is L. Now, when we consider a single slit as a full entity, its shape is actually important. And for the discussion here, what we're going to do is we're going to treat the simplest case first. The simplest case is when the slit is long rectangular thing here. So let's say the x-axis goes through the center of this rectangular thing here, and we're going to consider the short dimension only. So this dimension here is d, so the height is d, and in regards to the width of this slit, we will actually ignore it. Another way of saying it is that for now we're going to assume that the slit is very wide, even wider than the beam, maybe, or yeah. So that's what we're going to assume. Okay, so then the diffraction that we're going to consider is going to be in the we're going to consider the xy plane and discuss the diffraction within that plane. So xy plane is the central object on which we will study the single slit diffraction. By the way, if you look back what we did for Young's double slit or end slit problem, in fact what we considered is also in those cases the diffraction in the xy plane. We didn't actually quite discuss what happens if you get out of that xy plane. And generally you can do that just by using the same principle, but math becomes slightly more complicated, and you can either do it using analytical math, or in general you can use the computer to calculate the diffraction pattern at all angles. For this discussion, considering the xy plane would be sufficient. So, by considering a very wide plate, or very wide slit, the only thing that we need to worry about is this d. So let's draw a diagram, just as we did in many other cases. This is slit plate, and that's the screen. That's the screen, and this is D. The width is D. And what we have now is that the beam will come let me use a different color here. The beam will come and hit the screen here. The beam will come and hit the screen here. So this is quite analogous to what we've been doing in the past, in previous lectures. And so now let's see what we can do here. Now, first of all, let me actually have some comments here. So a single slit problem is actually a difficult problem in general. Why is this? Because the, materials actually modify the electromagnetic field around them because of the interaction between light and materials. This is actually quite severe in the case of a metal in the microwave region. So it's actually a very challenging problem, although some nice solutions are known in the literature. And so in general, single slit problem is not very simple. However, if you go to the optical range for visible lights, the single slit problem can be approximated very well in the following manner. So the main approximation is that this slit plate doesn't actually do anything except blocking the light and letting the light through. So this is essentially what we assume so far. We are making this assumption very explicit in the context of a single slit diffraction, because this assumption does break down severely in the case of microwave diffraction on a metallic slit plate. Now, with this simplified assumption, we can go ahead and calculate the single slit diffraction in the following manner. And in order to explain this, let me redraw that the opening part here. So what I'm going to do, I'm going to just I'm going to note that this is the opening of length height d. Following the idea of calculus, I'm going to divide this opening into many segments. So consider these short blue lines as my ruler with equal spacing, and then I can divide the dimension of this height into, let's say, from 1, 2, and n. So by doing this, guess what we just accomplished? We accomplished dividing the single slit problem so that it becomes an n slit problem, and we actually know how to do the n slit problem. So that's the idea, and this is the reason why we're dealing with a single slit diffraction problem as the last problem, or almost the last problem. So let's look at this n slit problem here. So then what I'm doing is that there's a slit 1, there's a slit 2, this void here, and then up to slit n. So they are all touching one another. Doesn't matter. We can treat all of these red points as as a source for a spherical wave. We can do just like in the n slit problem. So what we can do is we can actually use the mathematics that we used in the n slit problem. Okay, so let's see how we can do it. First of all, what is the slit spacing? That's important, right? We need to know d. In this case, we have to measure from the center of this red one to the center of that red one. And so what is the slit spacing here? So that's clearly the same as the distance from top of that red circle to the top of the second red circle. And because we have divided the opening into n pieces, so the d here is now capital D divided by large N, capital N. So that's D. And so that's it. So we got D, small d expressed like that, and the number of slits is capital N, and we can use I equals IR sine square n delta over 2 divided by sine square delta over 2. Now note that delta is kd sine theta. But in this case, when we actually understand a single slit problem as an n slit problem, d is not constant. It's actually dependent on n. And so when we actually multiply n, capital N to delta, what happens is that because small d is capital D over n, and then we are multiplying this, so what we get is k capital D sine theta. Now this we will define as beta, and this is actually a better parameter to use in the case of single slit. Instead of delta, this is a better number. Just notice that considering the single slit problem into as an n slit problem is an artificial picture, just for mathematics. And this beta makes much more sense as a parameter that characterizes this experiment, because it actually, beta doesn't depend on capital N, number of slits. And the results that we calculate here, we would need to follow the idea of calculus and consider the limit in which n goes to infinity. So that's just remember the calculus idea that we're using is a mathematical device. There are really no fixed number of slits in the n slit sense. At the end we need to take capital N to infinity to get exact result, just as in any calculus problem. So this beta is the central parameter here, replacing delta, because delta in this case is a phase shift between adjacent circles, but these circles become smaller and smaller as we take capital N to infinity. So delta is not a good parameter. It keeps changing as a function of n. Okay, so much for that. So now let's look at this. Sine square delta over 2. Delta, notice that delta here is k is determined by lambda, so it's determined by experimental parameter there, and sine theta is the angle at which the beam comes to the screen. And small d here, small d is actually an artificial parameter that goes like 1 over n. So for a given value of capital D, you can see that the small d will eventually go to 0, very, very small length scale, no matter what this k value is. When n goes to infinity, delta goes to 0, no matter what the angle of theta is, no matter what the value of k is, because d, small d, goes like 1 over n, this will go to 0. So that means we can approximate this sine square delta over 2 as delta over 2 squared. And then we're almost done here. The numerator here, you can notice that n delta is beta, so we can replace that. And so then I equals IR. Let me actually replace this delta with beta, because beta is the intrinsic parameter. So then so beta over 2 squared, and then the numerator is sine squared beta over 2. Because we replaced delta square with beta square, where beta is n delta, so we need to multiply here n square. But that's not a big problem. And IR, you remember the IR is actually the intensity of the beam coming from one slit, right? One slit in the n slit problem. In this case, IR is not constant. Is actually because we're dividing the beam, this opening into n artificial segments. Each point actually has 1 over n of the total amplitude, and because of that, IR being proportional to amplitude squared, IR actually scales like 1 over n squared. So that means IR times n squared, that's actually a number which is independent of n. So that's good news. So we can replace this IR times n squared as I0, which is a fixed number. So that's it. That's what we got. Okay, so let's write down what we just got. It's exciting to be able to get that result without doing too much work, because we've been doing a lot of work. So sine squared beta over 2. Let me actually don't square it yet, and then denominator was beta over 2 squared, and so this is the whole thing squared. That's the result here for the single slit. And beta is k times capital D sine theta, where capital D is a slit height. Now, this is slit height, but if it's a horizontal slit, then you can call it width. So this would apply for the horizontal width of the slit in the previous slide's diagram as well. If we assume that horizontal size is some finite number, we can apply this formula in the horizontal direction as well. In the in the x z plane. Okay, so this I0 here is indeed the intensity at 0 angle. Why? Because when theta becomes 0, beta goes to 0, and by using L'Hopital's rule, then you can prove that sine beta over 2 divided by beta over 2 goes to 1 when beta goes to 0. So the I0 is the reference intensity, meaning the intensity at 0 angle. So there it is. So let's make a plot of this function as a function of beta. Before we do that, let's take a note. The delta parameter is basically beta over capital N. And we know that from the n slit problem, the spectral function, the intensity function here is periodic as a function of delta with period 2 pi. Now here, delta 2 pi, delta equals 2 pi, that's period. So if delta goes from 0 to 2 pi, then beta goes from 0 to 2 pi n. So that's infinity, isn't it? Right? Because n, capital N, goes to infinity. So in terms of beta, this is not a periodic function at all, because the period becomes infinite. Non-periodic. And that's quite obvious, because beta over 2, that's not a periodic function. So basically beta goes from negative infinity to infinity, and this just shows a certain behavior. That's one period. Another thing is that where is the minimum value? So when we use this delta a parameter in the context of the n slit problem, we know that delta equals 2 pi m. That was the principal maximum condition, and then the minimum occurred when minimum intensity corresponded to 2 pi m plus 1 over n times 2 pi, 2 over n times 2 pi, and so on and so forth. In this case, we can see that these minimum values, because these minimum values correspond to increment of delta, which is 2 pi times n, we can see that in terms of beta, that increment should be 2 pi. And so here is the graph. It's an even function of beta. So if you can draw it on the right, and the left will look just the same. So when beta becomes 2 pi, it becomes 0. And that's obvious, actually, even without doing this. If you got this function, then when beta over 2 equals integer times pi, sign goes to 0, so that's where you will get the minimum intensity. And then there's 4 pi and 6 pi. So you get some intensity here. And as beta goes to a large number, you can see that the denominator increases whereas the numerator has the magnitude that is bound below 1. So you expect that these peaks actually gradually become less and less high. So the height will decrease as beta goes to the right, and when beta goes to the left, you basically have a symmetric situation here. Well, it's not quite symmetric, but please view this as a symmetric function, which it really is. From the grating discussions, we remember that the principal maximum intensity is much higher than the maximum intensity of the second maximum on the side, and so the same is true here. And if you actually plot this function using Wolfram or something like that, you can see that the second maximum peak here is about 0.05, about 5% of the principal maximum at the center here. And then the next one, the third maximum here, is about 2%. So it's pretty low. So this diagram is somewhat not to scale, because in this diagram, this one looks like almost 20%. So it's not so. It's only 5%. So it should be 4 times smaller. But that's pretty hard to draw. So that's why this diagram is not really to scale. But But anyway, so you get the sense, right? And so single slit diffraction pattern looks like this. And what's striking about this is actually it's very different from double slit. You remember the double slit pattern? In the double slit pattern, the maximum peak intensity has 1, and then the maximum actually repeats. So the intensity pattern is very uniform, and the intensity actually is a periodic function, and each maximum peak has the same width. It's not so for a single slit problem. Just as in the grating or n slit problem, look at this. The central peak is twice wider, and it's huge compared to others. So to an approximation, we can actually ignore all other side peaks here. We can just choose to characterize this single slit diffraction as as a central peak, because the side peaks here, they are quite weak. If you didn't quite follow what I was saying about the difference between single slit and double slit, don't worry about it too much, because I'm going to actually speak about it in detail at the end of this lecture. But right now, let's discuss the physics of this single slit result. To do that, let's discuss the minimum intensity condition here in terms of beta here. So minimum intensity condition is beta equals 2 pi times, let's see, what should I do? 2 pi times n or m? Not sure. Let's use n. And n equals plus minus 1, plus minus 2, dot, 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 dot. So that's the minimum condition. So if I just follow this notation here, hold on a second, there is something wrong here. This 0, no, this should start from 1. I think I said from 1, but what I wrote is not consistent with what I said. So if you follow here, this only accounts for positive values of n going to infinity, but clearly the left one also needs to be accounted for. So the n goes from -1 to -infinity as well. And let's write this in the form that involves lambda, just as before. K equals 2 pi over lambda, so 2 pi cancel out, so that means minimum condition. D equals, D sine theta equals n lambda. So now that's, in the case of single slit, minimum intensity, and in fact this minimum intensity is 0 intensity. So superficially, this minimum intensity condition is sort of the opposite to the double slit maximum intensity condition. I mean, it is the same as the maximum intensity. If you replace this capital D with a small d, in the case of double slit, representing the slit separation, then recall that in the case of double slit, small d sine theta equals n lambda was the maximum intensity condition. In the case of single slit, you have a similar expression here, capital D sine theta equals n lambda, where capital D is again the dimension of this single slit, the width or the height of the single slit. You actually have a minimum intensity. So in this sense, the meaning of this equation, the same equation is reversed completely between single slit and double slit. But also, as we just as we noted some minutes ago, when n equals 2 and 3 and 4, that's not really important, because n equals 1 is here. This is n equals 2. n equals -1 here. So what's important is that this n equals -1 case and n equals 1 case, because all other side peaks are so weak, they are not important. So that's it. That's the main discovery here. And this minimum, the first minimum on the left and on the right, basically it can be written as d sine theta equals lambda, and in this case d sine theta equals negative lambda. So what did we just find? Let's actually summarize the most salient feature. The most salient feature is that, well, just like in the grating case, and slit case, the most important feature is the central peak. Or in the end grating, end slit case or grating case, this corresponds to a principal maximum. And then there's, of course, weaker side peaks. Weaker side peaks will be ignored for this discussion. That doesn't mean that you cannot dream of some cool scientific experiments to do with those. I mean, they could be useful. It's just that for this discussion we will ignore it because it's not as important. It's not as intense as the central peak. The central peak has the width, which is controlled by this angular spread theta. So there is a size on the screen, let's say y, and this theta, how does it get determined? Well, we just found out this is determined by d sine theta equals lambda. So that's a very important formula there. And let's say this distance is L, as we have been assuming in these lectures. So then y equals L tangent theta. So that means theta increases, y increases. So that's how size increases. Let's ask one question here. For a given wavelength of lambda, in order to have less spread on screen, do you need a large d or small d? What's the answer? And the answer is, of course, large d. That may be a little bit counterintuitive, but that's what it is. If you want to have a sharp spot on the screen, use a big slit width. If you want to have a very blurred image on the screen, use a very small d. Okay, so that's the that actually tells you the wave nature of light, and this is common to all waves. To width, what happens is that if you localize a wave too much, it'll spread very quickly. However, if you don't localize a wave too much, if you allow it to have a spread in the real space, in the position space, then it will not spread as much. It will spread just a little bit, maybe, but it will spread much more slowly. Then it'll spread when it's localized very, very severely. So that's actually the wave nature. That's the nature of all waves. So let me summarize here. If d is large, then theta goes down according to that equation. So it suffices to discuss positive thetas because negative theta is symmetric. And if d goes down, theta goes up. So this actually, you can see the effect of this. You can see in classroom demos. If you use a slit with a narrow side vertically and then long side horizontally, then the spot that you will see will actually look like this. And then there will be some side bands, so some weak side bands here, and then here. You'll see those. You'll see those things. But the point is that it'll be thin horizontally, it'll be long vertically. So that's coming from this. Okay. Now we discussed this rectangular slit. An important type of slit is another important type is actually a circular slit. Why is it important? Well, I don't know. Circles are nice. So what is a circular? What is the diffraction pattern from a circular slit? If you have a circular slit, the diffraction spot that you get is also circular. That much is obvious, no? Because of the circular symmetry, the diffraction pattern should be the same in all directions on the screen, and that's different from this rectangular slit case, right? So what you get on the screen is what's referred to as airy disk or airy pattern. What it is that well, there is a central peak, and then there is a weak side band, side peak, so that it will be very bright here. Let me see. Very bright here, and then it'll become kind of weak, and it'll fill in. And black is dark, and then it'll be somewhat bright here. I'm just trying to. I don't know. This is my feeble attempt to draw the intensity here. I'm failing here, but anyway, you get the point. So this central peak is very bright. So let me just fill in there. For this discussion, let's again ignore this side band, which is kind of faint here, right? The faint side band. We will just take this central peak, and this central peak, again, the angular spread is given by a similar formula, and this theta, and it doesn't change much, but it changes a little bit. So for the circular slit, this sine theta equals 1.22 lambda. So that's a well-known result from the mathematics of airy pattern. You can go on, and you can go on to ask the question, what kind of if I have a slit that looks like a banana slug, what kind of diffraction pattern will I get? Well, in that kind of case, maybe the best thing to do is to calculate the diffraction pattern using a computer program. But one thing is for sure, no matter what kind of slit you have, any slit, let's say that you have banana slug or whatever, and no matter what kind of slit you have, you can define some sort of linear dimension that characterizes that's the slit size. If that's the case, then the size that the pattern that you see on the screen, the angular spread is given by number, which is on the order of lambda. And you will notice that in future physics courses, physicists really like this wiggly symbol here. It means approximately, or more exactly speaking, it is on the order of. So this means that d sine theta could be 1 lambda, or 2 lambda, or maybe 3/2 lambda, and things like that. 1.5 lambda, which is what I mean. But it would not be like 100 lambda. It would not be 0.01 lambda. Okay, so that's what it means. And the fact that we don't know exactly what the proportionality constant, oftentimes is not that important. What's important is that this d sine theta is given by a number which is on the order of lambda, and that's the main effect of a single slit diffraction.